one skill that chemists need to use in the lab is to be able to use data to determine chemical formulas for compounds. We try and do this all the time, and this is something that's often represented in the media. You have some sample, you take it to the lab, and you try and figure out what was in it. Well, it's not quite as easy as they often make it seem in TV and movies, but it is possible. If we have some experimental data, such as the mass of a lot of different elements that were found for a particular compound, we can use this to determine empirical and molecular formulas using some simple steps. First of all, let's say we're given grams of an element after they broke down a compound. We can use this to determine the empirical formula, so that's the lowest whole number ratio of the elements, using a few simple steps. We're going to take whatever grams they gave us, we're going to convert them to moles. We know how to do that. We're going to write what's called a pseudo formula, which is where we're going to use those moles as subscripts for a chemical formula. And then to get whole numbers, we're going to divide all those subscripts by the smallest one. If we don't end up with whole numbers at that point, we can multiply our subscript by some small whole number to get rid of any fractions. And we're going to see an example of this. So sometimes you're given data in terms of grams. So for instance, you had 2.75 grams silver and 1.22 grams oxygen, and turn that into an empirical formula. But sometimes you're given a percentage instead. It was 40% hydrogen, 60% carbon, something like that. So if you're given a percent, all you're going to do is pretend those percents are grams. You're going to say, well, if I started with 100 grams of the sample, then 40 grams of it would be hydrogen, 60 grams of it would be carbon. So you're just going to call it grams and then still do the same thing. So whether you start with grams or percentage, you're going to follow the same basic steps. Now, once you get to the end of this, you're going to have an empirical formula, that smallest whole number ratio. But what's more useful is to have a molecular formula. And if you have one extra piece of information, you can actually figure that out as well. So we can, that should say can, bad on me. We can convert empirical formulas to molecular formulas if we are given the molar mass. Now you might ask, well, how would we know the molar mass if we didn't even know what it was? But it turns out there are ways to determine this. In Chapter 5, when we're talking about gases, we'll see how we could use experimental data to actually determine the molar mass of a compound. So that is possible. And we can use that to convert an empirical formula into a molecular formula. So recall that an empirical formula is just the simplest ratio. So the molecular formula is just some multiple of that. So if we had an empirical formula CH, you could have a ton of molecular formulas. It could be C2H2, C3H3, C4H4, etc. Just as long as those numbers were the same, so that the ratio was a 1-to-1 ratio. So you can figure out what number goes here just by looking at this problem. You take the molar mass, which has to be provided to you, and you divide it by the empirical molar mass, which is the molar mass of whatever empirical formula you've ended up with. And then whatever that number is, you just go plug into your formula. So let's look at an example. Let's remember our basic steps. Convert to moles, write a pseudo formula, divide everything by the smallest number. And then if you have a molar mass, we can do this extra step. So let's look at how we might apply this. Fructose is a common sugar found in fruit. Elemental analysis of fructose gave the following mass percent composition: 40% carbon, 6.72% hydrogen, 53.28% oxygen. The molar mass of fructose is 180.16 grams per mole. Find the molecular formula. So when we do this, we really have to do this in two steps. First, we need to find the empirical formula using those first three steps. Convert to moles, write a pseudo formula, divide by the smallest number. Then we'll find the molecular formula. Molecular. Yeah, that says molecular formula. So when we're doing the molecular formula, that's when we do N equals the molar mass over the empirical molar mass. So it gave me this molar mass, and I'm just going to put that in my back pocket because I'm not going to need that until step 2. So I'm not going to do anything with that right away. Instead, I'm going to follow the steps to get my empirical formula, which is where I take these guys, I convert them to moles, write a pseudo formula, divide by the smallest number. So we have percentages, but we're just going to call them grams because we could pretend we have 100 grams of sample and then those would all be grams. So we're just going to convert each of those grams to moles. So carbon, I have 40 grams, and for 1 mole carbon, I look at the periodic table, and it's 12.01 grams. So my grams cancel, and I get 3.3306 moles of carbon. Then I'm going to look at hydrogen, 6.72 grams of hydrogen, and for every 1 mole, I have 1.008 grams of hydrogen. So my grams cancel, and I get 6.667 moles of hydrogen. All right, now last one, I'll do oxygen. So I'm starting with 53.28 grams of oxygen. For every 1 mole of oxygen, that is 16.00 grams. And so I get 3.330 moles of oxygen. Okay, so now I have converted them all to moles. So now I'm going to write a pseudo formula. So when I say write a pseudo formula, what that means is I'm going to write a formula that looks like CHO. And for the subscripts, I'm going to use the numbers I just figured out. So C gets 3.33, and we'll just round that to 331 right there. Hydrogen gets 6.667. Oxygen gets 3.330. So this was step 1, convert to moles. Step 2, write a pseudo formula. Step 3, divide everything by the smallest number. So these are pretty much the same number, so it doesn't matter which one I pick, but I'll do 3.330. So I'm going to divide every one of these by 3.330. And that'll give me some new subscripts. So I'll still have CHO. So these divide and give me basically 1. Same thing with the oxygen. And 6.667 divided by 3.330 gives me 2. So I have C1H2O, or we can just write that CH2O. So this is my empirical formula. So that's step 1, check. If it had just asked for the empirical formula, I would be done. But it did not. It asked for the molecular formula. So we've done step 1, empirical formula. So now we're going to determine the molecular formula. So we need to figure out this N by dividing the molar mass by the empirical molar mass. So we have our empirical formula. So now we need to figure out what N is. So we're going to do the molar mass divided by the empirical molar mass. So the molar mass it gave me up there was 180.16 grams per mole, and that has to be provided. That was given to me. That's the only reason I know that number. For the empirical molar mass, I'm just going to look at this and add this up. So for the, make a note down here, empirical molar mass, I have a carbon, that's 12.01. I have 2 hydrogens, which are each 1.008. I have 1 oxygen, which is 16.00. So I add those up and I get 30.026 grams per mole. So that's the empirical molar mass, just the molar mass of that empirical formula. So I get 30.026 grams per mole. So those cancel. I'm just going to get a number out of this, 180 divided by 30. So N is equal to 6. And so now I'm going to take this empirical formula, or maybe I can think about it with this one because I have the ones there, and multiply each of these subscripts by 6. So this is going to turn into C, 1 times 6 is 6, H, 2 times 6 is 12, and O, 1 times 6 is 6. So my molecular formula is C6H12O6. Again, the only reason I was able to do this second half is because it provided me with the molecular molar mass. If they had not given me that, I couldn't have gone any further than this. But because they gave me the molar mass, I was able to do this extra step, part 2, where I found out the actual molecular formula instead of just the empirical formula. Now, one thing I did not demonstrate that I just want to go up and make a note of is this point right here. Sometimes after you divided all subscripts by the smallest one, you might end up with something like C1.5 H2, something like that. So you've divided all your subscripts and you would end up with something like this. We can't have a 1.5. We need to have whole numbers here. So what we would do is multiply everything by a small whole number to get rid of any fractions. So 1.5 we see, okay, I could multiply that by 2, but I have to multiply all the subscripts by 2. So I would multiply all the subscripts, and this would turn into C3H4. For instance. So if at step 3, after you do the division, you have a 1.5, you're just going to multiply everything by 2. The only other fraction you might see, or decimal rather, is something like C1.25. Let's say we had, should be an H. Something like this, C1.25H1. In that case, we're going to multiply them both by 4, so that would be C5H4, for instance. But those are the only two possibilities you might see, 1.25 and 1.5. The 1.5 you multiply by 2, that gives you a whole number. The 1.25 you multiply everything by 4, and that gives you some whole numbers. We didn't have to do that in the problem we demonstrated, so I just wanted to point out that once in a while that will be necessary.